Hello everyone, welcome back to my YouTube channel. In today's video, we will be going over computer number systems in its entirety for the ACSL Junior contest. Our regular counting system is called the decimal system, or base 10. This is because we have 10 fingers. So normally in our everyday lives when we count things, we have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have 10 digits. In ACSL computer number systems, they will test you on 3 other number systems: binary, octal, and hexadecimal, which are especially useful for computers. Binary is also called base 2 and has 2 digits, 0 and 1. Octal is also called base 8 and has 8 digits, 0 through 7. Hexadecimal is also called base 16, or just hex for short, and has 16 digits. Now you might be wondering, 10, 11, 12, 13, etc., those are 2-digit numbers. What do we do about them? Well, those are replaced with the letters A through F. All right. So one skill that you'll be tested on is converting to base 10. In order to convert to base 10, we must first understand expanded notation. So consider the number 712. There is a 2 in the ones place, there is a 1 in the tens place, and there's a 7 in the hundreds place. This means that 712 is just equal to 7 times 100 plus 1 times 10 plus 2 times 1, which is equal to 7 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus 2 times 10 to the power of 0. So if you're not sure about how exponents work, go ahead and study up on that and then come back onto the video. Now, this over here, 10 to the power of 0, you need to make sure that anything to the power of 0, keep in mind, is 1. Okay, so anything to the power of 0 is 1. All right. Now, you try writing expanded notation. So write the number 8,593 in expanded notation. And by the way, this is just in our regular decimal or base 10 counting system. Okay. Let's do this together. So this is equal to 10. This is equal to, there's an 8 in the thousands place, 5 in the hundreds place, 9 in the tens place, and a 3 in the ones place. So we get 8 times 1,000 plus 5 times 100 plus 9 times 10 plus 3 times 1, which is equal to 8 times 10 to the power of 3 plus 5 times 10 to the power of 2 plus 9 times 10 to the power of 1 plus 3 times 10 to the power of 0. There we go. This is this in expanded notation. All right, let's continue. In order to convert numbers from binary, octal, and hexadecimal to base 10, we will use expanded notation. You might be wondering, what do you mean? We only learned how to do expanded notation in base 10. Well, let me show you. So, this binary number here, 10110, is in base 2, or binary. This little 2 represents that it's in base 2. And we want to convert this to base 10. So, let's first put this in expanded notation. Well, there is a 0 in the first place, a 1 in the second, a 1 in the third, a 0 in the fourth, and a 1 in the fifth. Just like in base 10, right, we just say 0 times, but here, instead of saying 10 to the power of 0, we will say 2 to the power of 0 plus 1 times 2, right, so instead of 10, we say 2 to the power of 1 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 3 plus 1 times 2 to the power of 4, and there we go. Okay, now we have it in expanded notation, and let's convert this to base 10. To convert to base 10, we simply just do the math, because technically this is already in base 10. So let's just simply do the math now. So we have 1 times 2 to the power of 4 is 2, 4, 8, 16, plus 8 0 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1, which is equal to 16 plus 0 plus 4 plus 2, which is equal to 22 in base 10. Right? So let's do this in base 8 now. We have 2 times 8 to the power of 2 plus 7 times 8 to the power of 1 plus 4 times 8 to the power of 0. Now, it's beneficial to go from right to left, but because writing on the screen is a little bit difficult, I just decided to do it from left to right. But it's beneficial to do it from right to left because you can start with 8 to the power of 0, then 8 to the power of 1, and 8 to the power of 2 after that. And now notice that here we used 8 to the power of 0 instead of 2 to the power of 0 or instead of 10 to the power of 0. So we used 8 this time. Right? So let's now just do the math. So this equals 2 times 64 plus 7 times 8 plus 4 times 1, which is equal to 128 plus 56 plus 4, which is equal to 100 and I believe 88. Okay. And if I got anything wrong, let me know in the comments. Okay. So next, let us do hexadecimal. Okay. So 2f in expanded notation is equal to 2 times 16 to the power of 1 plus f times 16 to the power of 0. Hold on. What is f? We can't multiply f by 16 to the power of 0. So remember that f is actually just 15, right? So a is 10, b is 11, c is 12, d is 13, e is 14, f is 15. So this is just equal to 2 times 16 plus 15 times 1, which is equal to 32 plus 15, which is equal to 47. Okay. Now it's your turn to try. Try these practice problems. I would say at least do one of each, and there's an optional second one for each. So pause the video, take a few minutes to do this, and then when you are ready to check your answers, unpause the video and I will reveal them. Okay, let's go for the first two. These are the answers. Okay, next. And finally, all right. And so especially when we get to powers of 16, it gets annoying. So here's a little chart to help you look at it. Okay. So now we know how to convert to base 10 using expanded notation. How do we convert from base 10? Well, here is the trick. In binary, if we're converting a base 10 number to binary, we will divide the number by 2, keep track of the remainder, keep dividing by 2, all the way, until the quotient is 0, smush the remainders together, and then you have your answer. Simple as that. Let me show you what I mean with an example. So we will need to convert 189 to binary. Let's do it. So 189 divided by 2 is equal to 94 remainder 1. Okay. 94 divided by 2 is equal to 47 remainder 0. 47 divided by 2 is equal to 23 remainder 1. 23 divided by 2 is equal to 11 remainder 1. 11 divided by 2 is equal to 5 remainder 1. 5 divided by 2 is equal to 2 remainder 1. And 2 divided by 2 is equal to 1 remainder 0. And 1 divided by 2 is equal to 0 remainder 1. So now, we start from the bottom and go up. And we take these remainders and smush them together. So from the bottom first, we have 1, 0, 1, 1, 1, 1, 0, 1. And it just so happens that this is the same going both ways, but you want to start from the bottom. And we know this because sometimes this top one, when you divide it, you will have a remainder of 0, and you cannot have a 0 to start a number, right? So we can have a 0. We can have a 0 to end the number, which would be the top one, but we can never have a 0 down here because there will always be a remainder. So yeah, that's why the bottom is first. Okay, so this is a handy little trick to convert from base 10 to binary. Now, our trick still works in octal. We simply just divide by 8 this time. So let's do it. Let's say 189 divided by 8 is equal to, I believe it is 23, remainder 5. Yes, and so 23 divided by 8 is equal to 2 remainder 7. And 2 divided by 8 is equal to 0 remainder 2. So going from the bottom up, we get 275 in octal. And again, my arithmetic may be a little bit spotty, so definitely correct me in the comments down below. All right. And then once again, our trick works in hex. So let's do it. We have 189. 189 divided by 16 is equal to 11 remainder 13, I believe. Okay. 11 divided by 16 is equal to 0 remainder 11. Okay. So 13. So first of all, 11 and 13 are two-digit numbers. So we first actually need to convert them into hex. So 13 in hex is equal to A is 10, B is 11, C is 12, D is 13, and 11 is B. So going from the bottom up, we have BD. Okay, so try out these practice problems. Convert 892 to binary hex and octal, and then convert 1073 to binary octal and hex as well. Pause the video if you need some time to work, and I will show the problems in 3, 2, 1, or show the answers, rather. All right, these are the answers to the first one, and these are the answers to the second one. Okay, so if you didn't get it right, go back and see what you did wrong, and try to fix it. Let's move on. We have learned how to convert between base 10 and binary octal and hex. So we did base 10 to binary octal and hex, and then binary octal and hex to base 10. But we've never learned how to convert between binary, octal, and hex just together. Now this is much easier than converting to and from base 10. To convert from binary to octal and hex, we simply group the binary number into groups of 3 bits, convert each group individually, and smush them together. It's the same thing for hex, but we do groups of 4 bits. This is best shown with examples. So let's convert. Oops. Okay, I had my things a little mixed up. Let's convert 100. Yeah, let's convert 100, 101, 0110 to octal and hex. So for octal, we group it into groups of 3. So I'm going to start from the right side. We always start from the right side. This is one group. The next group is 0, 1, 0. Next group is 1, 0, 0. And then finally 1. And you see that this is just 1, so we can add 2 zeros to the left side, and that will do nothing, but it'll make it into a group of 3. So then we convert these each independently. So we have 1, 1, 2, and 6. And so it's simply just 1, 1, 2, 6 in octal. All right. And for hex, it's very similar. So let me write this number out. Except groups of 4. So from the right side, this is a group of 4, this is a group of 4, and this is a group of 4. Convert individually. So this is 6. This is 1, 2, 4, 5. This is 6 as well. So we have 6, 5, 6, hex. Okay. All right. Now to do the other way, to convert from octal and hex to binary, it's the same thing. You just convert each digit independently and make sure for octal that they're in groups of 3, and for hex, they're in groups of 0. So add some zeros in the beginning. And yeah, just smush them all together. Smush them all together. All right, so for some examples, we have 2, 7, 4. Let's convert this to binary. So 2 is equal to 0, 1, 0. And make sure that we have the 0 here for the group of 3. 7 is equal to 1, 1, 1. And 4 is equal to 1, 0, 0. So in total, we have 0, 1, 0, 1, 1, 1, 1, 0, 0. And now we can see that this first 0 is not doing anything, so we can just have 1, 0, 1, 1, 1, 1, 0, 0. We can remove it. Now for hex, it's the same thing, except groups of 4. So 2 is 0, 0, 1, 0. F is 1, 1, 1, 1. And so our final result is 0, 0, 1, 0, 1, 1, 1, which is equal to 1, 0, 1, 1, 1 base 2. So if this was like F2, for example, we would have 1, 1, 1, 1, 0, 0, 1, 0. And that's when these 2 zeros actually start to make a difference. Okay. Now you try. Try these practice problems, pause the video, and when you're done, resume and check your answers. Okay, I'll assume that you tried these yourself. Here are the answers. Okay, the next topic that ACSL might ask about is colors. So the next topic ACSL will ask you about is colors. So we can use hexadecimal numbers to represent colors. The way we do this is in this format. We have hashtag 2 digits, 2 digits, and 2 digits. The first 2 digits is the amount of red in hexadecimal. So it can be 00 to FF, amount of red. The second 2 digits represent the amount of green, 00 to FF. And the last 2 digits represent the amount of blue, 00 to FF. White is FFFF because in computers and in light, white light is the combination of all different colors of light, and black is 00, 0, 0, 0, 0, because it is the absence of light. Colors can also be represented in base 10 using the RGB format, where X right here can be from 0 to 255. And if we actually, why do they choose 255? Well, because FF is actually equal to 255. And so together, there are 255 to the power of 3 different color combinations, which means that there are over 16 million colors in total. They're not going to test you on how many colors there are, but they will definitely test you on your knowledge of where is the red, where is the green, and where is the blue. Okay, so red first, then green, then blue. Okay. Finally, the last topic is addition and subtraction. Addition and subtraction with binary, octal, and hex is the same as regular base 10 numbers. So let's just go through some examples. First of all, binary. you simply just use the addition and subtraction algorithms and just do carrying over and borrowing exactly how you would before. So, except make sure you stay in the base that you're using. So binary, we have 1 plus 1 is 1, 0, right? 1 plus 1 is 2 in base 10, which is 1, 0 in binary. So we have a 0 here, and let's carry the 1 and put it here. 1 plus 1 is 1, 0. Carry the 1. 1 plus 1 is 1, 0. 1 plus 1 is actually 1, 1 now, right? So we do this. 0, 1, 1, 1, and that is our answer. Subtraction is very similar. 1 minus 1 is 0, regardless of what base you're in. 0 minus 1, you cannot do that, so we need to borrow this 1. This is now a 0, and this is now a 1, 0. So 1, 0, which is 2. 2 minus 1 is 1. Okay, 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. So we get 1, 0, 0, 1, 0. Okay, so let's do some octal examples. We have 6, 4, 5 plus 3, 7, 2. 5 plus 2 is 7. 7 plus 4 is 11, but that's in base 10, so we need to convert this to octal. 11 in base 10 is equal to, so if we divide it by 8, we get 1 remainder 3, and then 1 divided by 8 is equal to 0 remainder 1. So we get 1, 3, right? 1, 3. And so we'll put the 3 here, and we'll carry the 1 here. 1 plus 6 plus 3 is equal to 10. But that's, so 10 in base 10 divided by 8 is equal to 1 remainder 2. 1 divided by 8 is equal to 0 remainder 1. So we actually get 1, 2. So we have 2 and 1 here. And so our answer is 1, 2, 3, 7. Okay. We can now subtract. So 5 minus 3 is 3. We borrow 1 from here. So we have 5. The 6 becomes a 5. And the 4 becomes a 1, 4. Now, 1, 4 is not actually 14, right? Keep in mind that this is an octal. So 1, 4 in octal is actually equal to, I believe it is 8 plus 4, which is 12. So 12 minus 7 is 5, and then 5 minus 3 is 2. All right. Now let's get into a hexadecimal example. F plus 5. F is 15. 5 is 5, so 20. We get 20. And now 20 in base 16 is equal to, is equal to 1, 4. Okay, so if we do the divide by 16 strategy, we will get 1, 4. So put a 4 here and a 1 here. B plus 1 plus 1. Well, in this case, we can just simply count, right? We have B, C, and D. So D is B plus 2. C plus 6, we have, so we have A, B, C. C is 12. C plus 6 is 18, which is equal to 1, 2 in hex. So we have a 2 here and a 1 here. A plus 5. Well, let's try to count. A, B, C, D, E, F. A plus 5 is F if we just count on our fingers. Simple as that. So we get F2O4. All right, for subtraction, let's borrow something from this B, so it becomes an A, and this becomes a 1, 5. Now, this is not 15. Keep in mind, this is 1, 5. Okay, so there's 1, 16, and 5 ones. Now, this is 21. 1, 5 is actually 21. 21 minus 15. F is 15. So this becomes 6. So we have 6. A minus 1 is 9, because 10 minus 1. Again, we have to borrow. So 1, 6 is equal to 16 plus 6, which is equal to 22. 22 minus c equals, and c is 12. 22 minus c is 10, which is equal to a. Okay, and then 9 minus 4 is 5. So this is our answer. All right. I have some practice problems for you guys. So this is binary. You don't have to do all of them, but I recommend doing out the first two at least. Okay, I'll show the answers in 3, 2, 1. Hello? Okay. Octal. I'll show the answers in 3, 2, 1. And finally, hex. Answers in 3, 2, 1. All right. And that is the end of today's video. Thank you for watching, and I'll see you in the next one.